Okay, good day, everyone. I would like to introduce myself. My name is Surahman. I'm from State Polytechnic Samarinda, Indonesia. I was present in the 7th Borobudur International Symposium 2025 in conjunction with the third Interconnects 2025. Our title is Sustainable Internet of Things or IoT-based solar dryer dome to improve post-harvest drying and food safety for rural smallholder farmer. Okay, in the background and problem statement, as we know, the post-harvest losses reach 20 until 30% in tropical region due to open sun drying or traditional drying. The issue is weather variability, microbial contamination, and low efficiency. The farmer lack access to clean and consistent drying system. The research kept an objective. We find the most solar dryer lack of IoT-based control and hygienic design. So we develop and we in the objective, we develop an off-grid solar dryer dome or SDD with passive ventilation, solar PV, and IoT monitoring. A system overview for solar dryer dome in our research is number one, semi-spherical design to enhance air convection and heat capture. And number two, the power by 660 VP solar PV with 12-volt ampere battery. And number three is IoT system control for control temperature, humidity, and CO2 in real time. In the design specification of HDD, we develop DED, design engineering, the structural design layout as like in the picture, and also in the left and in the right side. The specification is the diameter 6 times 10 meter and the height 2.5 meter. Frame developed from steel, the cover from ultraviolet resistant and polycarbonate. And fans about 12 volts DC times 2, a sensor HAT31, MQ1 type, and sense air says H. The power about 660 VP and 12 volt battery. IoT integration. We develop IoT integration in the dashboard like in the picture, in the diagram. For environmental control in SDD, the specification is ESP32 microcontroller with MQTT data transmission. And number two is parameter monitored for temperature, NaH, CO2, VOCs, power, and voltage. In the dashboard, built with PHP and coordinator framework. And also we use a remote control for fans and system automation. In the experimental setup, we did the experiment up to 6 times and came up with the following. Number one, the crop for burning taro leaves and the leaf slice thickness 0.5 about 0.05 centimeter and 1.5 kilogram per tray because we use tray like 3 tray for runs. In the comparison, solar dry dome vs open sun drying, uh, in the duration consecutive days, 5 replicator per condition. And the result drawing performance comparison, like in this table, uh, drying and microbial count of leaves, bening leaf, yeah, and seed trial. In the method for solar dry dome, we got drying time 5 until 6.5 hours, but in sun drying, open drying, about 38 hours. So this table is the ratio comparison between the SCD and sun drying. Okay, the drying time, 6.8, about 0.4 hours SDD versus the 38 uh, hours open sun for open sun. The temperature about 44.5 degrees Celsius vs 32.2 degrees Celsius. For our age, 54.5% vs 79.8%. The TPC reduction 90% use malt, and the reduction 85%. This graph for comparison of HDD and open sun system. We know the temperature and area age profile during drying. The comparison is uh, the HDD is very effective. Result and discussion. The energy efficiency and off-grid operation, the energy generation and use statistic. This in the table, in the side is parameter, in the right is value. For solar panel capacity, we use a 660 VP daily energy generation, 2.64 until 35 kilowatts hours per day. The battery capacity 12 ampere and two battery. The energy usage is 2.1 kilowatts hours. The farmer feedback. We got three point from the farmer. Number one is protection from rain and insect. Number two, the reduce daily labor and higher products quality. And number three, and 20% higher market value for dome dried sleeve. The economic analysis. We also got the analysis four analysis. Number one is capital loss. Capital costs about 1,050 US dollar, maintenance 50 years, annual benefit 500 US dollar, labor and quality premium, a simple payback period about 3 years, and energy self-sufficient 100% solar. Key finding. Number one, stable drying microclimate, about 42 until 40% degrees Celsius, and air age about 60%. Number two, reduce drying time by 84.7%. And number three, 90 microbial load reduction. Number four, fully off-grid operation. And number five, farmer report high acceptance. For policy and practical implication, SDT support national climate smart agriculture initiative and scalable for farmer cooperative and rural SMEs, and then promotes clean energy transmission in agri-processing. For conclusion, number one, the solar dry dome enhance drying speeds, hygiene, and sustainability. Number two, the combined passive ventilation, solar PV, and IoT monitoring. And number three, recommended as a replicable model for rural post-harvest innovation. Okay, acknowledgement with thanks very much to Center for Research and Community Service of P3M State Polytechnic of Samarinda, Indonesia. And also we very thankful for partner farmer group and institution in East Kalimantan, Indonesia. This is the end my presentation. Thank you very much.